In this video, we're going to pick up where we left off with our free body diagram. So here we have our coordinate system on the right hand side. We have our free body diagram that is appropriately labeled, and we're ready to move forward. Now, what we can do now is we can start working in actual data that we've been provided, and this was data provided on slide number 5, to start the estimates of all of these forces acting on our original system. The one vector I don't have labeled here right now is the weight vector, and that's because I'm going to work in the actual values. So here we see that the weight of the leg is calculated from the mass of the leg, which was given to us at 4 kilograms, times the acceleration due to gravity, which is negative 9.8 meters per second squared. And when we do the math, we have a value of negative 39.2 newtons, and that indicates and confirms that the weight is acting downward in a perfectly vertical manner, and that's how we always represent the weight of any object. Now we have our three other vectors, none of which are perfectly vertical or horizontal. That means we have to apply vector resolution. In other words, we have to take all of our vectors here that are neither perfectly horizontal or vertical and break them up into x and y components. And I'm going to start with the distal part of our system and take a look at the force of the elastic band. So what I've done here is I'm just going to zoom in, and I'm going to ignore the weight FPT and FR, and I'm just going to redraw this distal portion of the lower leg and foot. And to recreate these forces, we have a 150 Newton resultant force that runs through the actual band, and we were given the value of 150 newtons at a 20-degree angle. Now, vector resolution means that we're going to break up our resultant vectors into perpendicular components to the resultant vector. In this case, it's the 150 newtons. And perpendicular components means that we form a rectangle from the tip through the tail of the vector, and the lengths, the sides of the rectangle represent those component vectors. So what we see here is we have a vector that's proportional to the vertical side of this rectangle, and we have another vector that's proportional to the horizontal side of our rectangle. And now what I'm going to do here is I'm going to move forward and actually calculate the length of this vector and the length of this vector. So I'll start with the vector in the x direction. We know that this vector has is going to be proportional to the magnitude of the resultant, 150 newtons, but it's going to be part of the 150 newtons. So this value will always be less than 150 newtons, provided that 150 newtons is at some angle greater than 0 from the lower leg. And we're going to use the cosine function because we want the adjacent length to the angle of 20 degrees. When we perform our calculations here, we find that we have a value that's negative 141 newtons. I put the negative sign here because the direction of this vector indicates that it's going in the negative direction, because at the start of this problem we had identified positive to the right. We'll do the same thing with our vertical vector here, and that's our force in the y direction, which again is proportional to the resultant of 150 newtons, but it's the sine, which is the opposite length to the angle of 20 degrees. And when we calculate this value, we're going to get negative 51.3 newtons. Negative because the arrow is pointing downward, which is opposite to the indicated positive direction for the vertical in our coordinate system. So now that we've successfully resolved our F band vectors, we can now represent those a little bit differently in our free body diagram. So when we apply the equations of equilibrium, we have our three equations. We're going to sum up all the forces in the x direction. Then we're going to sum up all the forces in the y direction. Then we're going to sum up all the moments of force. And when we add all of those up, they will equal to 0. So redrawing our free body diagram here, we have 51.3 newtons. Note I didn't put the negative sign here when I label this vector here, this component vector, because the arrowhead already indicates it's going in the negative direction, so we don't have to add that negative here. We have the horizontal component of the, or rather the x component of the elastic band at 141 newtons. We have the weight of the lower leg and foot at 39.2 newtons. And we have our force of the patellar tendon. Now, as we resolved the F band into X and Y components, we have to do the same thing for the force of the patellar tendon. And it will have a force of in the Y direction, and it'll have a force in the X direction as well. And note that these two forces are perpendicular to each other, the X and Y, forming that rectangle from the connecting the diagonal from the tip through the tail of the resultant vector. And recall that we also had a resultant vector that we don't know what the direction is. We made an initial guess, but we do know that it will too be resolved into X and Y components. So here we have the reaction force in the Y component and the reaction force in the X direction component. So now that we've resolved all of our forces into X and Y, we can now selectively move through our equations of equilibrium, and we always start with our X direction. So we always state the equation. We always write down the sum of the forces in the X direction will equal to 0, and you can move the 0 to the left hand side, and then you start adding up all of the X forces. And so what I like to do here is start on the distal end. You could start on the proximal end as well, but I like to typically start on the distal end, and I move from the right to the left or from the distal towards the proximal, and I start accounting for all of the horizontal directed forces. So here we have I've encountered a horizontal force that's of magnitude 141, and that was the X component of the band. I keep moving. I see the weight, but because that's vertical, I just skip over it. I ignore it. And I continue until I find another horizontally directed force, and that's the X component of the patellar tendon, and I have an X component for the reaction force in the X direction. Notice here, the first statement, I don't have negative signs here. Because we are adding up, all we're doing is substituting symbols at this point, but when we're ready to input numbers, then we would reflect whether those are going in the negative direction or the positive direction. And so the only data that I have so far is that I have the horizontal component for the elastic band at 141 newtons, but it's negative. So here's where I bring in the negative sign. I'm going to add that to the X component of the patellar tendon and the reaction force. So this gives us our first equation of our equilibrium step. So now what we do, we have a problem, and the problem here is we have one equation, but we have two unknowns here. We don't know, we weren't given the force through the patellar tendon. We're given the angle, but we're not given the resultant force of it, and we're not given the reaction force. So with those two unknowns, we can't solve it. We would need at least one more equation to match the number of unknowns. So at this point, we just take our one equation, we set it aside, and we move to the next equation of equilibrium, which is our y direction. So we just repeat what we did on slide number 7, but with all the vertical forces. So we start once again, we write the sum of the forces in the y direction will equal 0. Then we move the 0 to the left-hand side, and as I indicated before, I like to start on the distal end and work my way proximal. And so I encounter a vertical force, which is the y component of the elastic band. Once again, I'm not going to worry about negative values right now when I'm just putting in the labels. I continue to move proximal, and I encounter the weight of the lower leg and foot combined. And I encounter the force of the patellar tendon in the y direction, and I put that in my equation. And then the last vertical force is the y component of the FR. Now we do have values here, we do have data, and when we start putting in our data, we start to reflect the positive or negative value of the numbers that we have in hand. So I'm going to do that right now. We know that we have a 0 on the left hand side, so we just carry that forward. And we did calculate in an earlier step the magnitude of that vertical component of 51.3, but it's going in the negative direction, so we bring that negative value. We're going to add that to the weight of the lower leg and foot, which we had determined to be 39.2 newtons in the negative direction. So we're going to add a negative to this negative. But now we have force of the patellar tendon in the y direction and the force of the reaction in the y direction. So what we've done here is we've added another equation, but in adding this other equation, we've added two new unknowns. The force of the patellar tendon in the y direction and the reaction force in the y direction, we don't know what those values are, and based upon the data that we have, we cannot calculate those. We have two equations, but now we have four unknowns, and so that poses a problem here, but we have one more equation to do, and we're going to do that on the start of the next video.